So in the previous class, we were looking at the yes, VSWR, right? The standing wave ratio denoted by S, correct? And also we could identify what will be the impedance at a maximum voltage position and a minimum voltage position. These are the equations, right? So let's proceed further. The next topic that's going to come will be the losses, right? What are the various losses because of one major issue that is called as a mismatch, right? Whenever the impedance of the line, that is Z naught, characteristic impedance, is not matched by the ZL, we have several types of losses coming into picture. Now let's look at the various losses. Again, they are uh, equations, and we use these equations to solve the problems related to the various laws. So theory part very less, but most of the time we get questions on the problem side. Okay, so this is losses due to the mismatch in a transmission line. So as we know now, if a transmission line is not terminated in a matched load, right, always it's a mismatch between the input and the output of the transmission line. So we call it as a lossy transmission line. Okay, so the fundamental idea is that, right, if the transmission line is not terminated with what is called as a matched load, so load is not matched, right, this is going to imply that there is a mismatch between the input and the output of the uh, transmission line. So we call it as a lossy transmission line. So by default, okay. Now there are various losses encountered, right? For example, we are going to look at the following losses one by one. The first loss will be attenuation loss. Second component is reflection, and the third one is transmission loss, return loss, insertion loss, etc. These are the various losses we are going to see. Okay, so we'll look at the losses one by one. The first loss is called as it's called as the attenuation loss. Right. So what is meant by attenuation loss? It is basically a measure of the power loss due to the absorption of the signal, right, by the transmission line. Okay, so this basically is a measure of the power loss. That is basically it's due to the absorption of the signal, right? Whenever the signal is sent over the transmission loss. So this is how we try to measure. Okay, so this is how we try to measure. Normally, okay, let me try to give an equation in dB. So the attenuation loss in decibels. Okay, this is equal to 10 log, it's power, so 10. Okay, whenever it's power, it is 10 log. If it is voltage or current, then that will be 20. It's a 20 log. Okay, so either 10 log to the base 10. 20 log to the base 10. Okay, so that's how the calculation goes. Now you try to measure, it can be power or energy. Some of the books will say that it is energy or it's power, doesn't matter. As the either they will give only energy or they will give only the power. Okay, so this is how it's represented. So this is EI minus, this is ER, all divided by the ET. All right. The R stands for the reflected energy from the load. Okay, so where, right, where EI represents the input. Okay, so input energy. Now we have ER. This is the reflected energy. Now reflected from, this is the load component. Okay, towards the input, and correct. So this will be the transmitted. Okay, fine. Then there is another loss. The second type of loss that is common in transmission line is called as a reflection loss. Loss number two, reflection loss. So again, this is another measurement of the power loss, but it is the power loss due to the reflection of the signal due to impedance mismatch. Okay, so this is a measure of the power loss due to the reflection of the signal, right? Why the signal reflects? It's because of the impedance mismatch. Okay, so due to impedance mismatch. All right, now, so the equation to calculate the reflection loss is like this. Reflection loss, again we measure in decibels. So since it is once again the power, this is 10 log to the base 10. The equation is EI divided by EI minus ER. Okay, so yes, EI is input energy, ER is the reflected. Okay, now that's a reflection loss. Then okay, we have another representation, that is okay, let me give the second set of equations later. Okay, only when we see. So let's move on to the next one. This is the third loss. This is called as the transmission. Right, now this is the measurement of the power loss due to the transmission that is happening through the transmission line. Okay, so measure of, yes, transmission of the signal through the transmission line. Measure of power loss due to the transmission of the signal through the transmission line. The correct. We measure again, it's a power, so power loss in dB. So 10 log, this is EI divided by ET. Okay, it's T, transmission. Okay, then let's move to the next loss. That's loss number 4. This is called as a return loss. Right. It's a measure of the power that is reflected by the transmission line. All right. So return loss is a measure of the loss of power due to the reflection. Okay, by the transmission line. Return loss in dB is 10 log to the base 10. It is it's incident divided by reflection, EI by ER. All right. So okay, actually we can measure it in terms of the voltage, right? So now you see this is 20 log to the base 10. This is Vs divided by VR. Okay, Vs and VR we know, right? So the in the standard equation, the voltage that is yes, whatever is sent is Vs, whatever is reflected is VR. Okay, so like that we can. Fine. Then the loss number 5 is the insertion. Yeah, please tell me. So the next loss is insertion loss, right? This is a measurement of the loss of energy through a transmission line compared to the direct transmission without using a transmission line. We have two concepts here, right? Let me assume that I don't use a transmission line. So again, you see, without a transmission line, how do you transmit? Maybe there is a question, right? So before writing the explanation of this, I'll give an example. Let me say I have an amplifier. Okay, this is an amplifier circuit inside. So I have some very complicated circuit, let's assume, right? Maybe a radio transmitter, right? I have many components, right? And at the end, I have a transmission. Sorry, I have an amplifier. Now let us assume that I directly connect this to the antenna. Okay, so now this is assume that this is the antenna. Okay, I have some antenna over here. So this is the one which transmits. Now you see there is no transmission line directly connecting the antenna to the amplifier. Okay. In the next phase, what I do, right? I use the same amplifier, but you see antenna is here now. Okay. Between the two, I use a transmission line. Okay. So maybe I can try to represent the whole antenna by using a load resistor over here, right? So now this is the one which is going to transmit your signal once again, but you see now I used a transmission line of certain characteristic impedance Z. Right, now we try to measure this. There is an insertion loss coming into picture, right? That is basically when you insert a transmission line between two components, certain amount of energy is lost. Okay, now you see previous case, there is no insertion loss because you are not using a transmission line, but there is a there is a bigger loss coming over there. In this case, you have much bigger loss because most of the time your impedances are mismatched. The amplifier's output impedance and your antenna's input impedance are not matched. So you have bigger loss coming into picture. There is a huge amount of loss over there. So you insert a transmission line. Yes, I lose some energy because of the insertion loss, which we are going to define now, but still it is lesser compared to my previous loss. So you see that, right? There is a loss. So we have to, we are discussing about the loss. So we'll write what is this loss, but practically this loss is lesser compared to the other losses if you don't use a transmission. That's why transmission lines are useful. All right. Okay. So let's try to write about the insertion loss. So this is a measure of the energy loss due to the insertion of the transmission line compared to the direct transmission of energy that happens without the transmission line. When there is no transmission line, right, you have some other loss, right? So you are comparing. So let's try to measure that insertion loss measured in decibel. Now it's not in terms of EI, ER, ET. Okay, so we use some other notation. So this is 10 log to the base 10. We write two component is two components. One is E1, one is E2. So I'll tell you what is E1 and what is E2 now. So where the first component is E1. This is the energy received by the load when directly connect to the source without the transmission line. I don't use a transmission line. Okay, so when you don't use a transmission line, what is the power that is received or the energy that is received by the load? Direct reception of the power. Okay, so E1 represents the energy that is received by the load when the transmission line is not used, right? There is no transmission, right? And the E2 is the opposite one. This is the energy that is received by the load when the transmission line gets inserted. Okay, all right. Now, so we know that there are so many types of losses coming into picture. Now, out of which one of the major issue is the power loss. Whenever you transfer the power from source to the load, right? If the resistance of the load is not equal to that of the source, then I have a problem, right? This is my major issue in any of the circuit, right? It is not just between the two different circuits. It is even true between the components of our circuit, right? I have a radio circuit, let's assume radio receiver, right? From starting from antenna has an output. It should match the first filter we use, normally a low pass filter, right? That filter's input and the output of the antenna should match, otherwise you lose. Right. Again, after the filter, maybe I'm going to use a multiplexer which multiplies the carrier signal with the output. Right. Again, that multiplier circuit should also match its resistance with the previous component, and the resistance of that whole component should match my next whatever comes. Right. Maybe another filter, like that. So each and every component should match the resistance over. This is true, right? This is the example which I can give for the components of a circuit that should match their resistances. Internal resistances should match. That's the first case. And the second case, let's take two different devices such as a charger and a mobile phone. Okay, you see they are completely different components, right? But if you want your mobile to charge as quickly as possible, right, the output resistance of the charger should match to that of the input resistance of the, yes, right, mobile phone. If that happens, yes, you can charge as quickly as possible. Ultimately, you see the high power chargers are coming in market. Ultimately, they are trying to match, they try to take out a lot of power, a lot of current from the supply. That's first thing. And whatever power that is generated inside that, right, it tries to deliver that completely to the mobile phone. That's all. There are two things to match when the high power circuit design requires two things. One is perfect matching of your impedance, and second one is how do you manage the high amount of current that is drawn from the source. Two things to be matched. If it is done, yes, we can even go beyond the 200 250 watts or whatever, right? Maybe it's going to come soon in future, but ultimately that's the thing, right? Draw more and more power, keeping the voltage constant. See, it's a 5 volts fixed, but the current is more. Correct? More and more current is being drawn, right? So how do you manage that efficiently? First thing. Second thing, how do you match the impedances? Two things. If it's possible to manage, yes, you can go for high power transmit. That also, it's ultimately a power transmission ultimately, right? Okay, now with that introduction, we move to the next topic, that is the impedance matching. Right, this is the ultimate goal of our transmission line. Why we are studying this? It's just because of this issue. Okay, now, so try to recall, there was some concept called as a maximum power transfer theorem, somewhere you might have studied. Okay, that is another version of the same concept, right? So anyway, I don't want to bring that concept now, because that statement is completely different, right? We may not be able to correlate what we had studied and what statement I'm going to give now. Okay, so there was some theorem by the name maximum power transfer. Ultimately, that's also a concept of impedance matching. That's all. Okay, just remember. Fine. Now I'm going to make a statement. If you want to have the maximum amount of power to be transmitted from the source to the load, right? So what is the condition? The resistance of your source, basically impedance of your source and impedance of your load should match. Correct? Okay, so that's the first point I'm going to write here, right? That is okay, for the maximum power transfer from source to the load, right? The impedances of source and the load should be, I'll write same, right? I'll write, I don't write equal because of some reasons. Normally, there may be slight variation in terms of, you see, on the source side, you may have uh, R plus JX, okay? R plus JX on the source side. On the receiver side, it is fine to have R plus JX or even R minus JX. That's why, okay? When you see, the magnitude is still same. That's why I wrote the word same. I'm not writing equal. Okay, they're not equal. R plus jx is not equal to R minus jx. Okay, but if you take a magnitude, yes, they are same. That's why I wrote the word, the load and the source should be same. Okay, so it's the same in that sense. If you want, you can recall the word magnitude, right? Magnitudes must match, right? Doesn't matter if you have a plus jx minus jx, absolutely fine. Okay, this is what is a practical case. I'm going to come to that point in my next sentence. So uh, the practical issue is this. You see, we discussed about one point at our in our very first class, maybe that is the energy which you want to transfer from one point to other form, other point, source to load. You have the loss resistance. You can save it, right? Two components. One is a inductor, one is a capacitor. Correct? Now you see that's the important point which we are going to use now, right? The reactance of the load should be equal to that of source, right? Just now I mentioned, in the sense the magnitude must match, but ideally we expect opposite in direction, opposite in sign, not direction, sorry, opposite in sign. This is because, you see, I'm using an inductive source. Okay, source which is inductive in nature, that means it is R plus jx. All right, the load should be able to store whatever it is giving, so I'm expecting R minus jx because capacitor is going to store, correct? So from the source, I'm trying to give out the energy R plus jx. So I already know that inductor is something like which is going to convert the energy which is present in the movement of the electrons, correct? So that has to be stored on the receiver side, correct? The load side. So load should have a capacitor over there in order to store whatever is coming, correct? So that's why this is important. This is, again, this is a very practical issue. So I'm going to write one statement now. Just understand and just try to relate that to what I told just now. Okay. So this is the reactance of the load must be equal to the source in magnitude. Okay, it should be equal. That means x, I should have x on even the other side, whether it is load or source, that's fine. Okay, it should be same in magnitude, but right, it should be opposite. It should be opposite in the sign, right? So I can try to write it in this way. So the RL should be equal to RS. So load resistance is equal to load, the source resistance. That's okay. Okay. And on one side, I can have the plus JX. Okay. On one side, let me assume that this is source or load, doesn't matter. I write plus or minus. When it goes to the other side, it should be minus or plus jx, correct? Because plus jx becomes minus jx on other side. If at all you have minus jx on this side, other side is plus jx. So magnitude is same, opposite in the sign. I hope this is clear, right? That means if the source is inductive, load should be capacitive, correct? That means if the load is capacitive, the source should be inductive, and the vice versa. That's also true. Okay, now, right, whenever this particular condition is satisfied, we can say that yes, the impedance has been matched. Okay. So our ultimate goal is that, okay, I want to achieve this particular condition, right? Resistances should be same. Inductance, if at all I have an inductance on one side, it should be minus of that. Okay. Or if at all it is minus jx, I should have a plus jx on. So whenever you try to bring that in place, yes, we can say that impedance is matched. Perfect matched impedance. So I can simply write this means impedance matched. Right. Okay. Now I'll come to the problems once again, right? As of now, I just talk in term. I try to talk in terms of the impedance values like resistance, inductance, capacitance. Those terms I brought. But what are the actual problems we face when we design a circuit? I'll come back to that in the very next moment. Very next moment, I'll come to that. Okay. So as of now, in terms of the basic components, what do you mean by impedance match? Yes, we know now. Okay. Now, in order to achieve this, we basically have a lot of options available, right? Even up to the levels of what you call inside the VLSI circuits also we can do the matching. Okay. You might have studied various circuits for impedance matching when you studied maybe FET circuits, BJT circuits, etc. Right? Right? Do you remember any name of uh, can you name any one circuit only if you remember, otherwise it's actually not related. I'm just asking, are you able to recall any circuit which does the impedance matching of you can name BJT circuit or FET circuit, anything is fine, only if you recall, otherwise no problem. Okay, yes, right. So we have many circuits to do. That's good. All right. Now I'll come to the components that are referred as the impedance matching devices, right? Or the those transmission line, in specifically coming to the transmission line, we call it as a impedance matching lines. Okay, so impedance, for the purpose of matching the impedance, you can even use the transmission lines, and those lines are called as impedance matching lines. Impedance matching lines. So as our discussion is restricted to the transmission lines, I use only this term, okay, impedance matching lines. So they are the components of the transmission lines used for only they have only one purpose, okay, used for impedance matching. Impedance matching, fine. Okay, now I come to the actual problem. Okay, that is say now let me go back to the example I have used just now. So that is, I have an amplifier, okay, and uh, I have say an antenna, okay. Maybe I have an antenna. Let me try to write it in this way. Okay, fine. So you see, I have, anyway, I'm not showing the ground here. Okay, so I have only one single point. I just want to connect this with this. So anyway, there is a ground line coming ultimately, right? So everything is with respect to ground. Okay, so when I look into this amplifier, there is a resistor. I can see that there is a resistor. Okay, when you look inside the into the ports of the antenna, once again I can see the resistor, correct? Now ultimately these two should be same. That's the whole concept. Fine. Okay, let's come back now. See, the amplifier circuit what you design is for this example, this is the source. I want to transmit the energy that is output from the amplifier that's coming out, I want to transmit that power to the antenna. Okay, so amplifier is my source, the antenna is the load. Okay, that's fine, right? Okay, now, so normally most of the cases, right, this is the scenario we face. It can even be, it can be true for the component before my amplifier. Okay, I may have a multiplier circuit, so two signals come, I multiply, and that signal is what I'm going to give as input to my amplifier. Okay, possible, you again see two resistors over here, right? One resistor here, one resistor. Again, there is a, it's the same problem. My multiplier circuit is the source, amplifier becomes the load form in that case, right? This is true for each and every component of our circuit. Okay, all right. So anyway, I'll just erase that part, because anyway, it's the same replica. Fine, I'll just erase. Okay, now coming back, for every circuit you consider, every load, or sorry, every source is going to have a fixed impedance, because, right, I say that because the each and every component that you use inside your amplifier, right, normally if you remember what are the components you use in an amplifier, maybe a BJT, okay, or an FET, right, depending upon which mode you are operating your device. Okay, device in the sense that active device, such as amplifier, sorry, inside the amplifier what you use, the BJT, FET, or any other CMOS circuits, whatever, right, you use over there, they have their own resistances, correct? I cannot alter that, because that's already manufactured. I'm simply purchasing from a vendor, I'm using in my circuit. I cannot alter that. There is no chance that you can change it, correct? So you're okay with that, right? So like an IC, I bring an IC, I use it in my circuit. I don't have any control over the resistance of that. So the ultimate point is that anything that you use inside your source will have a fixed impedance, correct? Fine. Okay, that's okay. We are okay with that. Very similar to that, you see antenna, right? Most of the time, until and unless it is a very simple circuit, okay, let me say that I'm designing a FM transmitter. Fine. In that case, I can try to use my own antenna. I can take a wire, I can wind it, right? I can make a small winding of that wire and I can use it as antenna. That will work. But if you are going for a high frequency transmission, right, gigahertz range or something very specific range in which you want to do, or maybe a satellite communication, something like that, very specific application, very high frequency, we cannot build the antenna by ourselves. That's the problem, correct? Which means you will once again purchase, right? I need this bandwidth, I need this particular specification, give me an antenna. So they will give an antenna, you bring it and you connect, correct? So that again means that you don't have any control over this. That antenna is going to, or that's again, I'll use the general word, that load, right? So this is a load, this is a source. So as of now, we understood that source resistance is fixed. Similarly, the load resistance is also fixed. That means definitely they are not equal. Source is completely different, manufactured by some vendor, right? You get it somewhere. Load is also available from somewhere else, right? They are not going to be equal. So there is no question that I am connecting them directly. Okay, so that's the most important point. Why cannot you connect? This is the answer. Now, so what is the solution? I need a circuit in the middle which performs the, right, the impedance matching. That is absolutely necessary, because those two resistors what you see there are not equal. Fine. So when I come to a very small circuit, right? Maybe the whole circuit, like a whole transmitter or whole receiver, I want to build in 1 mm into 1 mm. That's the smallest region you can see. Within that, I want the whole circuit. Then there is no question of using another bigger component, right? For that whatever the impedance matching, I cannot use a bigger device. Even the transformers are impedance matching devices, but I cannot use it here because my whole circuit is 1 mm into 1 mm, right? So in such case, what is the solution? You go for the transmission lines, impedance matching lines. So they are very small, yes, right? You can build lesser than the size of whatever your whole dimension. You can use the transmission lines of that size. But so that's what is the upcoming or the higher topics, microwave transmission lines. So as of now, we have not touched that. It's we are still in the basics, right? Which is simply the transmission line. Okay. All right. So we understood this. Let me write that sentence so that when you read it, you will understand. Okay. So I'll write 2 points that we discussed so far. Right. So this is first one is about the signal sources. What we discussed about signal sources, they have fixed impedance. Have fixed impedances and impedance matching, right? When I say I have a fixed source, what is the ideal case? Ideal case is that, okay, choose a load whose resistance is equal to the resistance of the source, correct? So problem looks very simple, right? Okay, I know that, okay, I have a source whose output resistance is say 10 ohms, fine. Now the point is that you should select a load which is also matching 10 ohms. That's all. That's my problem, right? But normally that is not going to happen. Okay, right. So I'll write one point here, which signal sources have fixed impedance. This implies that uh, we should choose a proper load. Okay, proper load of okay, I understand. I don't want to write further. Anyway, it's understood. Proper load means whose resistance should match to this one. Okay, right? But what's the actual problem? The load impedance is also a fixed value, correct? But the load impedance is also a fixed value. Then we have a problem, right? So this means now now the question cannot be formed in such a way that can I design a source which matches this? Impossible, because source is mostly designed first. All right. So source is already you have from where it's decided that, okay, I'm going to draw the energy from this device. Okay, so there is no question of going back, right? Though I know that load impedance is some different value, I cannot go back and redesign my amplifier or the source. Impossible. Fine. So now the actual problem comes into picture, right? I need a impedance matching, right? So that means we need the impedance matching circuit. Right. Whenever our requirement is very small in dimension, the whole circuit size is very small, means I cannot go for discrete component that matches the impedance, such as, right, even the we can say that the yes, we have the transformers of very small size, but again you see the example I gave, it is 1 millimeter into 1 millimeter. That size you don't get any transformer, right? So the only solution you have to use the transmission lines over there, which can be brought up into any size, right? So again, there are other aspects. Anyway, I have not discussed that now, but I'll bring those words as well now. So whenever I try to use a transmission line system, right, this matching is actually important to achieve the required standing wave ratio. Okay, to avoid the unwanted power losses, or the maybe you can even call it as a leakage of the current or voltage, whatever, right? So in order to achieve the desired efficiency, or maybe you want to have no reflection or something like that, right? So you see, what are the advantages of using the transmission lines over there? You can achieve the impedance matching, plus you can achieve the required standing wave ratio, required efficiency, right? Many parameters can also be matched. Okay, so by using the transmission lines as impedance matching circuits, right? What are the advantages we can do, right? We can get the required standing wave ratio, right? We can match the required z naught, right? In a sense, you can match the z naught, right? You can even match the voltage standing wave ratio, right? You can also match the power requirements, the losses. You can try to design that, right? Whatever is the amount of loss, you want to ensure that this is what is the maximum amount of loss. When loss comes, you can also have the efficiency, right? Etc. So those are the advantages of using the uh, transmission lines for the purpose of uh, impedance matching. Okay, now I'll go one step ahead. So if you properly terminate the transmission line with its characteristic impedance Z naught, right, then its impedance input impedance remains at Z naught when the frequency is completely varied. Okay, so what do you call that term? Do you remember? I'll give a time to you to think. I'll write one sentence. Okay, so yeah, I'll repeat my question. And my question is that there is a circuit. In general, there is some circuit, and I keep varying its input frequency, not voltage, not current. Okay, input frequency I keep on varying, right? Assume, you can assume that voltage and the currents are constant if required. Okay, actually those values have nothing to do with my question. That's why I said you can think that it is constant, no problem. Voltage, currents are constant, but I keep varying the impedance. Sorry, frequency, my mistake. Frequency, I repeat. Yeah, input frequency is varied. All right. Now, if there is a circuit to which I am actually giving the input, and the circuit's resistance or impedance is not changing with the frequency. As I change the frequency, my circuit's impedance is a constant. What do you call that kind of, what is the state of the circuit? There is no name for a circuit. Okay, I'm not asking what is the name of the circuit. What is the state? There is a state of that circuit wherein input frequency change does not affect its impedance. So what is that state? Okay, think of that. You have 1 minute time. I'll write something here. Okay. So if I can write, okay, if the transmission line is terminated with the ZL that is equal to Z naught, this implies the impedance remains Z naught always, even when the input frequency is varied. Okay, what's the answer? Hmm. Lossless, but I'm writing a Z over there. Maybe this Z is R plus J, R minus J. So there is a R coming into picture. So uh, no, that's the point here. I have not used the word R here, right? Because there can be R as well. Okay. That's why I have not written, right? There's something like just jx and minus j. I didn't write that. I use a z here because it can contain r plus j or r minus j, or only r or only j, jx. Okay, so it's like that. That's why we use the term z here, impedance. Okay, maybe in some lab experiment you might have done one experiment where you keep current and voltage fixed and you keep varying the frequency of your input. Maybe just try to recall. I think there is one experiment somewhere. I'm not very sure which lab it is, but it will be there somewhere. Okay. Uh, Maybe I'll tell you what is the output so that I can bring out the word from. I'll make you to recall the word which I'm looking for. This is something like whenever you vary the frequency, maybe the current will reach a maximum value and then comes down, right? Current increases, reaches a peak value, then comes down. What is that? What ex Yeah, current slowly increases initially as you increase the frequency, right? Just try to recall, right? I'll try to draw. Maybe that's what will give you an idea about that. This is my experiment. I increase the frequency, I measure the current in the circuit. Let's assume it's not only current, you can even do this for the voltage. Okay, but the voltage waveform will be different. I'm discussing about current because it is easy to recall. Current increases and comes down. So you have something happening here. What is that? At a f naught you have something highest current I max, then two other frequencies, fh, something like this, maybe fl. So this is right, some value of current, maybe 0.707 I, something like this. Have you done? Okay, no problem. Have you heard the word resonance? Now are you able to recall that word? Right, so you had something called as a resonating frequency, right? So in the resonating frequency, the resistance is going to change. But here you see it is opposite. Impedance remains the same. In the above line which I mentioned here, right? You can see that, right? If the transmission line is terminated with so and so condition, impedance remains constant. Impedance remains constant means it is non-resonant. The circuit is a non, that means, right, the circuit becomes non-resonant. What is the use? I'll tell you. This is actually a very practical situation, right? I'll just write the word here. So it is non-resonant. The word to be used is non-resonant. Okay, right? Now I'll come to the actual issue. So you understood what is it, right? Okay, so what happens if a circuit is non-resonant, as you change your input frequency, right? Because you see, maybe most of the time we apply the transmission line to match the impedance between an amplifier and an antenna. 99% of the time, this is the application. Okay, where do you use? You go for megahertz range or beyond that, gigahertz range, right? The ultimate microwave frequencies or beyond that is where you are going to apply this. Okay, you see what is the frequency? It's in 10 to the power 6, 10 to the power 9, that range. Okay, so small change, 1 gigahertz changed into 2 gigahertz, you see frequency changes by a huge amount, correct? Right? I may send maybe whatever is my signal, right? But I want to do a frequency modulation, let's assume, right? Again, it's not a practical application where you use a frequency modulation at that high frequency. It's not that. But I want to give you a simplest example. So I'm trying to make out this example by myself. Okay, so you see, I am using two different frequencies. One is 1 gigahertz, another symbol I want to send at 2 gigahertz. Okay, so 1 gigahertz to 2 gigahertz, there is a huge difference in frequency, correct? Right. Now you see, when the signal, if the circuit is non-resonant, when the signal is 1 gigahertz, my circuit looks like say 500 ohms, right? Because it has a certain frequency dependent resistance, right? When I'm sending 2 gigahertz, my circuit looks like 100 ohms for that. Right now, you see, impedance. Though you matched your impedance, it's of no use for you. Correct? I matched for 500 ohms, but immediately when I change the frequency, I have to replace the antenna by some other antenna, which is impossible. That's the major issue, right? So what we want a the impedance matching device should be right, non-resonant. That's the ultimate point. Now you see, we achieved that, right? So irrespective of what frequency you give at input, no problem. It has nothing to do with the impedance. Impedance will not change, fixed. So that you can connect an antenna of the fixed whatever resistance, right? No problem with the input signal. Whatever frequency you want, you send, no issue, right? Ultimately, that is the important thing which we wanted to achieve, and it is possible if you use the transmission line for this purpose.